So this set of videos is about radioactivity, P6, radioactive materials, and the first one is about what radioactivity actually is. But before we get into that, it's really important that you know about the structure of the atom, because radioactivity concerns a part of the atom, the nucleus. So you need to know about the nucleus before we can know about radioactivity. Now, you'll have covered this loads of times before, but there's nothing wrong with a basic recap. So the first thing we need to look at is our basic atom here. Now this is an atom of helium. Okay, now this is a helium atom. Now helium is pretty simple. It's the second smallest atom out there, and it has three main particles. It has three particles in there. The first one is this thing here, and this positive thing with the plus on, it's positive, which is where it says plus, is a proton. This green one next to it is neutral, so it doesn't have a sign, and it's called a neutron. Now, the protons and the neutrons in an atom are all grouped together in this little central part here, and this, with these two things in, is called the nucleus. And the nucleus always contains all of the protons and neutrons of an atom. Okay? There's one more particle that we need to know about, and that is the electron, and that's these small ones here that you can see. They're negative, which is why they've got a negative sign, and they orbit around the nucleus, a bit like the planets orbit around the sun. Now they're attracted to the nucleus because the nucleus is positive, and we know that positives and negatives attract, but they orbit in shells. Now the thing that tells me what an element is, or what an atom it's an atom of, is the number of protons in there. So the number of protons in a helium atom is 2. The number of protons in a different atom, say hydrogen, is 1. Carbon is 6. That's what determines that. The number of protons is usually, and also, well, if it's an atom, it is equal to the number of electrons. If it's not, then we call it an ion. But that's something for later on and more chemistry-like. Okay, so that's the basics of the atom. You should really know a lot about this already, but just really quickly, I'm going to go over now the properties of those particles that are in that atom. Now, the charge of a proton, we've just said, is positive. The charge of a neutron, as it's nu, is neutral, okay? And the charge of an electron is negative, and that's really important that you remember that. Now, all of the mass of an atom, basically, is in the nucleus. That means, all the mass. That means that the mass of an electron is basically 0. It's not exactly, but we can say almost 0, and that's what that sign means pretty much 0. Protons and neutrons are about the same mass. They're minutely different, but we can ignore that. And we say when we're talking about atoms that they've both got a mass of 1. Okay, so they're 1 each. So if you've got 2 protons and 2 neutrons, the mass of this here is 4. We're going to come on to that in a second. And finally, there's a location. Now, we've just talked about this. The location of the protons is the nucleus. That's all that they're always there. Neutrons are also in the nucleus. And the electrons orbit around in shells. So, hopefully we remember all of that. If you don't, make sure you know it, because this is really important, not only for your physics GCSE, but also for your chemistry GCSE as well. Now, radioactivity is all to do with the nucleus of an atom. That's where it happens. So we're going to talk more about the nucleus of different atoms. And we talk about what an atom is. There's a symbol for each one, and you'll have seen on the periodic table something that looks like this. Each element has a section of the periodic table that looks like this, with a symbol and 2 numbers. Now this symbol here, this is a C. This is the filament for the element. So for here, it's carbon. Now there's 2 numbers on this. The first one at the top is called the mass number. Now the mass number is equal to the number of protons plus the number of neutrons in the nucleus. So that means that in carbon there's 12 protons and neutrons. So not 12 of each, but altogether there are 12 protons plus 12 neutrons in terms of the numbers of particles. Now the next one here, the 6, this is called the atomic number. And that equals the number of protons. So we know here that carbon has got 6 protons, and if you add the number of protons to the number of neutrons, it's got 12 altogether. Now that means that it must have 12 neutrons, not 12, sorry, 6 neutrons, because 12 minus 6, the difference between the number of protons plus number of neutrons and the number of protons must be the number of neutrons. So number of neutrons is equal to mass number minus atomic number, and that's written really badly, I apologise, but hopefully you get the point. So for here it's 6. Now there's something called an isotope, okay? An isotope is a particle, I'll write this up here, is a particle that's got the same number of protons, or not a particle, an atom, same number of protons, but a different number. This is really hard to read, I apologise. Different number of neutrons. Okay? So the number of protons that an atom has tells me what element it is. So if it has 6 protons, it is always carbon. If it has 1 proton, it is always helium, not helium, hydrogen. So if you look down here, I don't know how well you can see this, but I've got 3 different particles. Now this one, I'm going to colour in these reds. These red ones I'm colouring in are protons. So these 3 particles, or atoms, have all got 1 proton each. I'm going to colour in my electron blue. They've all got 1 electron. Now the number of electrons is always the same as the number of protons because an atom is neutral. So if I've got 1 positive particle, I need to have a negative particle to balance that out. However, these particles have all got different numbers of neutrons. Okay, now my neutrons are going to be green. Now my first one, this is normal hydrogen. Okay, hydrogen as you normally see it. It doesn't have any neutrons. When I get on to the next one, I'm going to add a neutron into my nucleus. Now this is called deuterium. Now this is a type of hydrogen, but it's heavier than normal hydrogen, and it's got a neutron in its nucleus. That means we're going to write this differently. So my first one, if I look at this, my atomic number is going to be the number of protons, which is 1. My mass number is the number of protons plus the number of neutrons, which is 1 plus 0, which is 1, and H is my symbol for hydrogen. Now this is still a hydrogen nucleus because it's got 1 proton. So I'm still going to have the H here, and my number of protons is still 1. Now if I look at deuterium, if I add the number of protons and number of neutrons together, I get 2 because there's 1 neutron and 1 proton. Now finally I come on to this one which has got 2 neutrons. Now this is called tritium. And the words are probably making more sense now because you know if you think about French, un, deux, trois, deuterium and deux, tri, you know from tricycle, triangle means 3. So this here has got 3 particles in the nucleus, 3 protons plus neutrons, and only 1 proton. So that means that 3 minus 1, it must have 2 neutrons. So these are all isotopes of hydrogen because they've got the same number of protons, so they're still hydrogen, but they've got different numbers of neutrons, and that's a really important thing to remember. So the next thing I'm going to talk about is what radioactivity actually is then. We've talked about the structure of an atom, we've got the basics about what a nucleus is. Now I'm going to talk about what radioactivity actually is. Now this here is a really large nucleus. You can see there's lots of protons and neutrons. Now you can't see them in colour, but I'm going to do lots of pluses, and the pluses are protons, and then the ones that haven't got pluses on are neutrons, and I'm probably not going to do enough pluses in time. But you can see that this is a really large nucleus. There we go. So let's pretend that's all the protons in there, and there's a lot of neutrons there. Now some nucleuses, are unstable. That usually happens because they're too big, but not always. They're unstable. They don't want to be like that, though. They don't like being like that, so they try and make themselves stable. Now, unstable nuclei have got too much energy, basically, and they want to become stable nuclei. So they do that by emitting energy, okay? And they emit that energy in one of 2 forms. They either send out a particle, which has got kinetic energy because it's moving, or they send out a photon or a wave, which has got energy just for being a wave. So they get rid of their excess energy and become stable. And they either do it through a particle or a wave. I'm going to talk about those different types in a minute. Now this process is called radioactive decay. And we've got the definition of radioactive decay, just don't want to move that piece of paper too much, just here. Radioactive decay is the spontaneous change. Spontaneous means it happens at any time, it's random, in an unstable element. It gives out alpha, beta or gamma radiation. We're going to talk about those in a second. Alpha and beta radiation result in a new element. We'll talk about that later as well. So radioactive decay is the spontaneous change in an unstable element, and it does that by getting rid of excess energy, by throwing out either a particle or a wave. So if something's radioactive, that just means it's a material that produces radiation. So a radioactive material is something that produces radiation by changing its atoms or its nuclei because they're unstable. Now this process is not stopped by anything. There is nothing that scientists can do to stop this, not by chemical or by physical processes. So chemical would be things like burning. Physical processes are things like melting. So if you melt a radioactive element, it won't stop being radioactive. If you burn it, it won't stop being radioactive. There's no way to stop it being radioactive. It just won't stop it. It will always give off this energy. Okay, so I mentioned 3 different types of radiation, and I've got them here. Okay, the main types we're going to know about are alpha, beta, and gamma radiation. Now, you might recognise these words because they're Greek letters, and you might have heard of them before. Now, alpha radiation has got the symbol alpha, like that. So if you're tired and don't want to write alpha, just draw a little symbol there. Now, alpha radiation is simply a helium nucleus, and that means it's made up of 2 neutrons, which I'm going to draw a little N in, and 2 protons, which are positive. Okay, so it's a helium nucleus, or He, to be quick. It's a helium nucleus, okay? Now, because of that, it has a charge of +2, because neutrons we know are neutral, and protons have got a charge of +1. So together, that's got a charge of +2. Now, the next one we're going to talk about is another particle, and it's called a beta particle, and the symbol is like that, it looks like a B. It's the Greek letter for B, basically. Now, a beta particle is just a high energy, or a really fast, electron. So it's a really speedy electron. That's all it is. Now, because of that, that means it's got a charge of -1. Because we know that electrons have got a negative charge. So it's less charge than an alpha particle, about half the charge, but also the opposite charge. And then finally, we've got our gamma radiation, and gamma has got this symbol, like that. Now, gamma radiation isn't a particle, it's a wave. And you've probably heard of it before, because in P2, you did the electromagnetic spectrum. And all it is, it's the most energetic part of the electromagnetic spectrum. And it's got a really high frequency, a short wavelength, and that means it's high energy. So it's a high energy photon. That's how you need to know what a gamma radiation is. It's high energy photon. So unlike the alpha and beta particles, which are particles, gamma radiation is a photon, it's a wave. Now this means that it's got a charge of 0. So we know things like light don't have any charge. Remember, light's a photon as well. Now, in terms of speed, if I draw a line like this, an arrow like this, I can label this increasing speed. So alpha's the slowest, beta's the middle one, and gamma's the fastest. So this is increasing speed. Can't spell today. The opposite way, so this way, would give me increasing size. So we know that protons and neutrons are much, much bigger than electrons. So that means that 4 of them together must be much bigger than 1 electron. So an alpha particle is bigger than an electron, or a beta particle. Then photons are the smallest things basically in the world, and gamma ones are the smallest of all. So a gamma wave is smaller than a beta particle. So increasing size is that way, increasing speed is that way. Now another difference between them is what they penetrate through. Now an alpha particle, which is this purple one here, is really easy to stop. If I send an alpha particle towards a piece of paper, it'll be blocked by that piece of paper, it can't get through. Beta radiation, because it's a bit faster and it's smaller, it's less ionising, we'll talk about that another time as well. That can get through paper quite easily, but it will be stopped by a thin sheet of aluminium or some plastic, things like that. Alpha will also be stopped by your hand or your body, any skin. So beta gets stopped by a thin piece of aluminium. Now, gamma radiation is really, really penetrating, and it finds it really easy to get through anything, basically, except for many, many, many metres of concrete, or, as we've got here, quite a thick piece of lead. So a couple of centimetres of lead will stop most of it going through, but you'll still get a little bit. So gamma radiation is really penetrating. It's the most penetrating. It'll get through pretty much most things. It travels for infinity through the universe until it hits something, such as a really thick piece of lead, and it might stop it a little bit. So they're the main things you need to know about alpha, beta and gamma radiation, and they're all summarised on this table here, just thought it would be a bit easier to see. So we've got our alpha radiation. It's made of a helium nucleus, which is 2 protons and 2 neutrons, and it looks something like this. It's the largest of the 3, but it's the slowest. It's got a charge of +2. Now, if there's nothing to block it, the range in air is about a few centimetres because it will just come in contact with some particles in the air and will ionise them. And once again, I'll talk about that later. That stops it. So it's only a few centimetres in air and it can be stopped quite easily by a sheet of paper. Now, outside of your body, it's not particularly dangerous. This is the important thing to look at because it gets stopped by your skin. However, if it gets inside of your body, it won't come straight out. It will stay inside your body and it will ionise some cells in your body. And that's not a good thing because that can lead to cancer, but we'll talk about that in a second. Now, beta particles, we just said, are high-speed electrons. They're just a single particle like this. They're really small. They're pretty fast. They've got a charge of -1 because it's an electron. In air, they'll go for a few metres before getting stopped because they will ionise some air eventually, but because they're so much smaller, there's less chance of them hitting an air molecule. They can be stopped by some aluminium or a few centimetres of plastic, and they can be quite dangerous both inside and outside of the body because they can get in a few centimetres into your skin and do something there, or if they're not going to get completely out of you. If it's inside of your body, they're not going to pass through you. They'll kind of interact with your body about a few centimetres in. So that's quite important to know. Now, our final one was gamma radiation. It's a high frequency or high energy photon, and it looks like this. It's the smallest one, it's tiny. It's the fastest because it travels at the speed of light. Beta ones basically travel at 99% of the speed of light, but not quite. It doesn't have a charge. It says range in air thousands of kilometres. It's probably more than this. It's like basically as far as it can go before it hits something like a thick sheet of lead or metres of concrete. And it's really dangerous when it's outside of your body, not so much when it's inside, because if it's outside, it's got more of a chance of passing through you and doing some damage on its way through. If it's inside of you, it's probably just going to pass straight out again. So it's more dangerous outside. So in the everyday atmosphere, you want to be near alpha particles, not gamma ones. If you're swallowing it, I'd rather swallow a gamma particle because there's more chance of it getting out without damaging me. So that's all. That's the basics of radioactivity. Next, we're going to go on to a bit more about the nucleus. But it's really important to know the structure of the atom and the 3 types of radioactivity and what radioactivity actually is.